So we're going to work on problem 13 in chapter 5 of the Marion and Thornton textbook. This is a problem where you're supposed to find the force on a particle that's inside a dust cloud, and we're assuming we have a planet here of constant density in the interior of the planet itself that's surrounded by a dust cloud that also has a constant density. So we're going to call rho 1 the density of the planet and rho 2 the density of the dust cloud. And we're going to need to find the force on some spacecraft that, say, is in some location here inside the dust cloud. And so to do that, we're going to employ the idea that we can find the gravitational field G, and then, of course, the force is going to be the mass of the ship times G. And so because it's spherically symmetric, the best way to find G is to use Gauss's law. So Gauss's law says that the flux of the gravity vector is equal to minus 4 pi G times the mass enclosed. So I've drawn my Gaussian surface here as a red dotted circle that is in the atmosphere. And so if I'm in the atmosphere, the mass enclosed is going to be equal to the mass of the planet plus the mass of the atmosphere that's enclosed. So the mass of the planet, since I have constant density, is going to be rho 1 times the volume of the planet. And then the mass of the atmosphere enclosed is going to be rho 2 times the volume of the atmosphere that I'm enclosing. Now, since the planet is being modeled as a sphere, the volume of the planet is 4/3 pi r1 cubed. And now for the atmosphere is also assumed to be of constant density, and essentially it's a shell. And so the volume that we need is 4/3 pi r cubed minus 4/3 pi r1 cubed. And the reason for that is that if I'm at this black dot is where my ship is located, I'm at some radius r, and the only bit of the volume of the atmosphere that I need is the part of the atmosphere that is beyond the radius of the planet, but inside of my red circle, or my red sphere. Okay, so I can say here that my mass enclosed is 4/3 pi times rho 1 r1 cubed plus rho 2 times r cubed minus rho 2 times r1 cubed if I pull everything out. So there's my mass enclosed. And then I would say, when I'm going to do the left-hand side of Gauss's law, I would say that there is spherical symmetry. And now the flux of the gravity vector is always negative. So I'm going to have G times 4 pi r1 squared, because when I think about how this is going to go, wherever I'm at, the G vector is going to point downwards, and the dA vector is going to point outwards. So in Gauss's law, it's always the flux. You're trying to count up the flux out of the sphere. And so these two are going to be in opposite directions, which yields this minus sign. And because I have spherical symmetry, the G is going to be constant everywhere at that same radius. And this is just not right. And what I need then would be the surface area of the sphere where I'm located. So this red sphere that I'm working at has a surface area of 4 pi little r squared. So little r is my radius to the sphere. So Gauss's law says I should put that equal to minus 4 pi G mass enclosed. I found the mass enclosed. So the 4 pi's are canceling out, and the minus signs are canceling out. So I have G is equal to 1 over r squared times 4 pi over 3 times rho 1 r1 cubed plus rho 2 times r cubed minus rho 2 times r1 cubed. So there is my expression for the G. And then, of course, the force would just be the mass of whatever my ship is times that G.